communication system needs easy and fast transmission of data from one place to another. Nowadays, we are using fiber optic materials in communication systems. In our class today, we are going to understand what is a fiber optic material and how it is used in communication systems. Okay, so fiber optics. This name was coined by Narendra Singh Kapali. He is a Indian American scientist in 1960. Now, first we understand what is the purpose of this fiber optic material or optical fiber material. Generally, we use these materials for the propagation of light waves. We understand how these light rays or light waves or light signals are going to be propagated with the help of these fiber optic materials. Suppose if we consider a light source, then the light coming from the light source is going to be propagated in all directions, but any source should be supported by a medium in order to stand there. If this is a light source or torchlight like this, then the light coming from this one, in general, we are going to have propagation in the forward direction, that is from in all these directions like this. The light comes like this. This is the light and this is the supporting medium. That is, generally it is going to be propagated in forward directions. Okay, it is a point source, ideal source, then it is propagated in all directions, but as we see here, it is the supporting medium, then it goes in the forward direction. Suppose if we make this light, or if we use a tube like structure light here, and if we make this light to pass through this tube like structure, then what happens here? That is, we are not sending these light rays in all directions, we are just allowing these rays to travel in a particular path. Then we can understand that it is going to be propagated through longer distance. Okay, and what is the purpose of this one means, this tube like structure means it is guiding these light rays to pass through a particular path. This type of material or this type of work is done by our fiber optic material or optical fiber material, and this is how we are going to give a meaning for that one. Fiber optics or optical fiber is called as guiding medium. Okay, optical wave guiding medium. It is going to guide the optical waves. It is called as optical fiber, is defined as optical wave guiding medium. Optical wave guiding medium is called as optical fiber. Now we study further about this one. Suppose if we take that in the form of a hollow cylinder like this, and if we allow to pass light through this type of structure, then what happens here? No doubt it is going to have reflections like this. Instead, if we take a solid material or solid cylindrical structure, and if we propagate the light, then what is the difference between these two? See, at each reflection, here it is hitting a hot surface. At each reflection, it is hitting a soft surface. When compared to this case gives less loss of energy. This gives this case gives less loss of energy, but the reflections are taking place in denser medium. The reflections are taking place in denser medium. And also we are going to consider, suppose for the propagation of light, the glass is the best material. That's why if we take the refractive index of glass as 1.5, that is, it is generally around 1.5. Then if you see various situations, suppose we are considering this case, when you compare these two, this is the best case. Now we are talking about this one. Now if you take this glass and if you take that one like this, and if you leave this one as 8, that is, the refractive index is 1.0. In the second case, if you take this material and around this material, if you take another material which is having the value at 1.25, the refractive index of this one is 1.25. Then in the third case, we take the refractive index as 1.49. It is 1.5 here and 1.49. If we compare these three, then it is the most soft medium, comparatively denser. This is close to this one. If we take the comparison between these three cases, then the best option is this one. The reason for that one is, no doubt, the light ray while traveling through this interface, it is encountering a change in refractive index, a great change in the refractive index. Here it is somewhat less. Here almost all the light is traveling within the same medium at 1.5 refractive index. That's why, as if it is, the light is traveling as if it is traveling in the same medium, the loss of energy is still lesser here. That is, we have to take two media such that the refractive indices are close to each other, and this gives a best structure for the propagation of light rays. Then we take about this type of structure. Before going to study about these refractive indices and how the light is going to be propagated through that one, we are first deal with the entire structure of the optical fiber. Okay, then for the first case, there is a, for the propagation of light, as we are sending light signals or light waves, for the propagation of light waves, only very thin material is sufficient. That's why we are going to have very thin structure for this one. That is central part. It is called as core medium. Okay, the diameter of core is expressed in micrometer. Very small value. It is generally from 10 to 50 micrometer diameter. Then the first one is called as, central part is called as core, like this. The next layer is called as it is covering this one core, it is called as cladding. Next one is called as cladding. This is core. Next one is cladding. Then next one is silicone coating. Silicone coating. Okay. Next one is buffer layer. This is buffer member. Buffer member. Next one is strength member. Strength member. And the last one is polythene plate. Polythene layer. The entire structure is like, see here, core, the central part, the light propagation takes place here. It is the denser medium, its refractive index is more. Then outside that one, covering that medium, we are having a cladding medium. Okay, the refractive index is close to this one but a smaller one. It is less denser medium when compared to core. Okay, these two are generally called as optical fiber structure. The entire dimensions of this one is about some 150 to 200 or 250 micrometers. Then up to these two levels, we are just talking about the propagation of light. Generally, it is made up of glass materials like silicates. Silica material is the best material. That's why the material is somewhat brittle. The next one is silicone coating. The same type of material as that of core and cladding, and it acts as the same layer, that is the same interface between core and cladding. That is, some of the core is sending the light and cladding is reflecting the light. In the same way, this silicone coating also brings some of the light again into the core and cladding structure, so that the quality of light is going to be increased. That is the purpose of this silicone coating. Then these three structures, we are just talking about only propagation of light and the material is brittle. Then next comes buffer member. It is acting as that strength member, as well as the refractive index is somewhat better, and it is a intermediate member between this strength member and these delicate parts. That is, to some extent it is going to have hardness, and the refractive index is in between this strength member and this silicone coating. Okay, that is, this acts as an intermediate member. Then in order to give the strength for the structure, we are adding this silicone coating, and the last one is we are covering this entire structure by a polythene layer. In order to protect from outer environment, we are adding this polythene layer at the outside. This is the entire structure of a fiber optic material, and this type of structure we are using. Now again we come back to this one. Okay, out of these layers we just talk about these core and cladding structures, and core is where the propagation of light takes place, and cladding is a less refractive index medium. Now, in order to consider the propagation of light through the structure, core and cladding structure, we make use of Snell's law. And the propagation of light through core or the optical fiber works based on the principle of this only. It is called as total internal reflection. From Snell's law, if a light ray is passing from denser medium to rarer medium, it is going to bend away from the normal. Okay. We are going to take denser medium here, and rarer medium here. Rarer medium here. If a light ray goes from denser medium to rarer medium, it bends away from the normal. It bends away from the normal. Then, if we increase the angle of incidence in the denser medium at one particular angle of incidence, if we slowly increase this one at one particular angle of incidence, it is going to graze the interface like this. That is, it is 90 degrees here, and this angle of incidence in the denser medium is called as critical angle. Okay, the angle of incidence in the denser medium for which the angle of refraction is 90 degrees is called as critical angle. Then, if the angle of incidence is greater than this critical angle, then it goes or it comes back into the same medium. This is denser medium, this is rarer medium. This is rarer medium, this is denser medium. This is how the propagation of light takes place within the denser medium. Okay, and that is when a light ray goes from denser medium to rarer medium, it bends away from the normal based on the Snell's law. It is given by n1. Snell's law is given by sin theta 1 is equal to n2 sin theta 2, where n1 is the refractive index of the first medium and n2 is the refractive index of the second medium. Theta 1 is the refractive index angle in the first medium, and theta 2 is the angle in the second medium. Okay, n1 sin theta 1 is equal to n2 sin theta 2. Whenever this, if we simply call this one as whenever this theta 1, say this theta 1 is less than theta c. This is theta 1 greater than theta c. This is the condition under which light is going to be propagated within the core medium. It takes place by multiple total internal. This process is called as total internal reflection. Why it is called as total internal reflection means, okay, it is totally reflected back into the same denser medium. Okay, as compared to ordinary reflection, this is having more energy. That's why it is called as total internal reflection. Okay, by making use of this one, we are going to have some calculations for this fiber optic material. Okay. It is a three-dimensional thin layer thread-like structure. The dimensions are very small. The core is almost all, it is equal to our human hair. That is the thickness of that core medium. Now, for our convenience, we draw the structure like this. It is a three-dimensional structure. Suppose let it be core, or I am going to draw here. Let it be core, and around which there is a cladding. For our convenience, we draw the structure like this. That is more core structure and less cladding structure. Generally, the core is very small and the cladding is very thin. Okay, but for our convenience, we draw the structure like this. Then the outer medium, generally it is air. That is called as launching medium. If this is the normal, then if we launch the light ray here, then at this point it is going to bend because this is the denser medium. If this angle is more than critical angle, it comes back into the shape, or otherwise it goes like this to the okay. And if we increase this angle here at one particular angle, it is equal to critical angle and it grazes the surface. it grazes the surface. Then if we still increase this one, the angle is more than critical angle and it comes back. That is, if we take this one as the critical position, all the light rays that are there within this one, they are going to pass through the core medium. The light rays which falls away from this one, they are not supposed to go through the core medium. And as it is a three-dimensional structure, suppose with this angle, if we construct a cone, this is called as, that is, all the light rays that are passing through this cone, they are going to be allowed to go to the other side by this core medium. Okay, this type of cone is called as acceptance cone, because this cone is accepting the light rays. Then this angle is called as acceptance angle. Is called as acceptance angle. That is the semi-vertex angle of this acceptance cone, or the maximum angle of launch up to which the light rays are accepted by this core medium is called as acceptance angle. We call this one as alpha m. For our convenience, if we draw the structure in a two-dimensional way, that is taking core like this and cladding like this, then for smaller angles it goes to the cladding. At a critical value it grazes the surface. If it is more than this one, they come back into the same medium. If we take this slide, that is critical ray here, then we are going to show only for this ray, okay, in order to have calculations. That's why we draw the angle like this. First, we are calling this one as acceptance angle. Okay, acceptance angle. We are representing that one with alpha m. Now we are going to take a critical situation. This is cladding, this is core. The refractive index of this one is N1 and the refractive index of cladding is N2. This is cladding, this is core. Now we take a normal here. If this is the critical ray, at this interface, this angle is theta c. We call this one as alpha m. The maximum angle of launch for which the light rays are accepted by this core medium. Okay, we are just drawing that structure. Okay. Now, generally it is 8, or we just take the refractive index as N0. Then, by using Snell's law, this is 8 launching medium, this is core medium. Okay, applying Snell's law between launching medium and core, launching medium and core. Okay, this launching medium refractive index is N0 into sin alpha m is equal to, we call this one as R, angle of refraction. Okay, the refractive index is N1, N1 sin R, N1 sin R. Then between launching medium and core, between core and cladding, between core and cladding. If we use this Snell's law, then in core the refractive index is N1, for core the angle is sin theta c is equal to, here this is angle is 90, then n2 sin 90 is 1. We call this one as equation 1, this as equation 10. Now we take this triangle, call this one as A, B, C. We extend this one and we draw a perpendicular from that point B. Okay. Then in triangle ABC or ACB, it is 90 degrees. Okay, it is 90 degrees. Then we can write R plus theta C is equal to, from triangle ACB, R plus theta C is equal to 90. Okay, test it. We substitute this one here. Sin R, for R can be taken as 90 minus theta C. From substituting in 1 in equation 1. Okay, then 0 sin alpha m is equal to n1 cos theta c, cos theta c. Now instead of this cos theta c can be written as n1 root of 1 minus sin square theta c. Sin alpha m or alpha m is equal to sin inverse of 1 by n0. What is sin square theta c? It is n2 by n1 root of n1 into root of 1 minus n2 square by n1 square. That is sin inverse or not into yes 1 by n0. Okay. Sin inverse of root of n1 square minus n2 square by n0. As it is a, generally we write this one as sin inverse of root of n1 square minus n2 square. This is the expression for acceptance angle. Then we are going to have one more meaning from this expression, or if we write simply this equation sin alpha m, we can write root of n1 square minus n2 square divided by n0, and this value is called as, see, if we take this triangle like this for an optical fiber, the light is entering like this. It is opposite side, it is our theta, then this is the whole biggest side, this is opposite side by highest value, that is a fraction. Okay, that is a fraction, and that fraction is indicating the light rays that are entering into the material. That's why it is called as aperture, numerical aperture. Aperture means a hole or which is going to allow light. Okay, what is that value means? It is given by sin theta. That is, it is called as aperture. That is, that amount of light, for that amount of light, the optical fiber is acting as aperture. It is just passing that amount of light from one side to another side. That's why this sin alpha m is called as numerical aperture. Okay, there is no problem in deriving this one. The second one is, it is called as numerical aperture. I am going to write here. We are having two quantities, acceptance angle and numerical aperture. Numerical aperture. Okay. It is defined as the light gathering capacity or ability of a optical fiber. Okay, it is given by sin alpha. Sin alpha. This is equal to root of n1 square minus n2 square. For practical purpose, we are going to simplify this equation. See here, it can be written as a square minus b square, a plus b into a minus b. That is root of n1 plus n2 into n1 minus n2. n1 minus n2. Then we know that the difference between these two is very small, or n2 is equal to n1. If we substitute n2 is equal to n1, we get 2n1. We should not take that approximation on this side. This is a small quantity, but not 0. That's why we confine that approximation only for this one. Then we write this one n1 minus n2. Then again we are going to divide and multiply this equation. We are going to divide and multiply this equation, that is sin alpha m is equal to root of 2 n1 square into n1 minus n2 divided by n. And we write this one as n1 into root 2 delta, where delta is called as fractional change of refractive index. The refractive index is changing from n1 level to n2. That is, what is the change means n1 minus n2. Okay, what is the maximum value of refractive index means n1. That's why this value is called as fractional change of refractive index. We can write this equation like this: sin alpha m is equal to n1 into root of 2 delta, where delta is called as fractional change of refractive index. Okay, this is how we are going to calculate how much of light is gathered and up to which angle the light is going to be propagated in that through that optical fiber. Okay, now we are going to study about different types of classification of these optical fibers. Generally or mainly, we are going to concentrate on two types of classification. One is based on refractive index profile, and the second one is modes of propagation of light waves. Okay. First, before going to that one, in order to understand something about this fiber material, we are going to have three types of classification. First one is based on material or composition. Material or composition. They are called as glass fibers. Second one, plastic fibers. See, first, in order to have propagation of light through this material, they found that silicates are best suitable materials. That's why generally they are going to use those glasses, but it is not a pure glass. They are going to mix some polymers for that one. Okay, then we call that type of structure as optical fiber or fiber optic material. That is, glass plus polymers gives this optical fibers or fiber optic materials. If the large percentage of the fiber optic material is glass, then we call that type of optical fiber as glass fiber. If we are having a considerable ratio for these polymers also, then we are going to call that one as plastic fibers or polymer fibers. Okay, these are the two classifications regarding composition. Then the second one is modes of propagation. Modes of propagation. Okay. Depending on modes of propagation, again we are going to have two types of classification: single mode optical fiber and multi-mode optical fiber. In the case of single mode optical fiber, the core dimension is very thin, so that it is going to allow only one type of propagation of light. That is, it is very thin, the diameter of the core is very thin, so that only one type of light rays they are going to be propagated. If the dimensions are large for the core medium, then there are so many modes of propagation. That is based on the diameter of the core, we can classify as single mode optical fiber and multi-mode optical fiber. Then coming to refractive index profile, again they are divided into two types: step index optical fiber and graded index the meanings. The names itself, they are going to give meanings. Step index, that is, we are having a fiber material. If we draw that structure in a vertical manner, then in the case we are going to have, if we take the refractive index along y-axis and the distance from the center of the core along x-axis, this is the distance. Then this is N2, this is N1, this is A, diameter of the core. Then the refractive index changes from N1 to N2 in a single step at the diameter of the boundary of the core. That type of optical fiber is called as step index. In a single step, it is going to change from N1 to N2. If it gradually changes from N1 to N2, graded means gradually changes. This is N1, this is N2, this is A. Then that type of optical fiber is called as graded index optical fiber. Then we are going to have combinations of the single mode step index, single mode graded index. Generally we won't find single mode graded index because here the dimension is very small. In that one we cannot, it is difficult to bring changes. That's why we rule out this combination. We are going to have single mode step index, multi mode step index and multi mode graded index, out of which in large number of cases we are going to use multi-mode step index and multi-mode graded index optical fibers. Multi-mode means it is going to allow large number of light rays in different modes, and these two types, multi-mode step index and multi-mode graded index. Now we are going to see propagation of light rays through this multi-mode step index and multi-mode graded index optical fibers. That is, we are going to consider propagation of light rays. Generally, the light properties are carried by electrical components. Writing only electrical components, the electrical vector can be written as E is equal to E naught into some exponential of J omega T minus K. This is how we are going to write an expression for the vibrations of electrical component. Then, if you take gradient index, multi-mode step index optical fiber and multi-mode gradient index optical fiber. In this optical fiber, if you take this one and this, if this is cladding and the central part is core, then it goes like this. The light propagation takes place like this. Okay, it is going to be reflected at the interface. This is cladding, this is core. Okay, in the case of multi-mode gradient index optical fiber, as the value of refractive index gradually changes, it takes place like this. At each and every point it is going to have a bending. It appears as if it is traveling in helical path. This is how the light is going to be propagated. That is, it looks like a reflective type. It looks like a refractive type. Then, if you give a signal here, then the light rays are reflected, and the light rays that are traveling in a straight line manner, they are going to go fast to the other end. The light rays that are having more distance path, they are going to have a delay in the reach. That's why if we apply this sort of signal, we are going to get a distorted signal here. This type of distorted signal here. If we come to this case, some light rays are traveling like this, some light rays are traveling like this. The refractive index is more here, the refractive index is less here. That is, the light rays that are traveling through greater refractive index, they are traveling greater distance. That is, they are having lesser velocity. That is, the light rays traveling lesser velocities, lesser distance are having lesser velocities. The light rays that are traveling greater velocities are having greater velocities. That's why they are going to come to the other point at the same time. If you give a signal of this sort, then we are going to have the same type of signal. There is no signal distortion here. Here there is a signal distortion. Focusing of light takes place here. There is no focusing of light. But if you calculate the numerical aperture value, then we are going to get that value as high for these types of materials. The numerical aperture value for these types of materials is low. Then coming to modes of propagation through these types of material, in the next coming few minutes, we are going to have a parameter called as V number. With the help of that V number, the number of modes are given by V square by 2 here. Here V square by 4. Because as the structures are symmetric, we have to have less modes of propagation through this one. Okay, this is how the propagation of this light waves takes place in these multimode step index optical fiber and multimode graded index optical fiber. Then we see what is meant by this V number. Suppose if we are having it gives the limitation for the wavelength or frequencies that are going to pass through the fiber material. Cutoff frequencies or cutoff wavelengths is given by this V number. Okay. Suppose if we are having a fiber material where we are having core and cladding, the refractive index of this one is N1, the refractive index of this one is N2. Now, wherever there is an interface, the light ray is reflecting back into the core medium. That's why at the interface, the effective refractive index is taken as root of n1 square plus n2 square. If A is the diameter of the core, then the circumference of the core is 2 pi A. The circumference of the is 2 pi A. If we take that circumference like this, or we draw the structure like this is 2 pi A, then how many modes are going to be propagated means, if we take a cross section, these are going to be propagated, these are going to be propagated. All the light rays which are having these types of structures, which are integral multiples of the wavelength of propagation lambda, they are going to be propagated. Okay, that is the effective path distance is 2 pi A into root of n1 square minus n2 square. N1 square minus n2 square. And this effective path difference should be equated to, if there are v number of rays in this one, that is surrounding this one, if we are having v number of rays, then v into lambda is equal to 2 pi A into root of n1 square minus n2 square, or v is equal to 2 pi by lambda into A into root of n1 square minus n2 square. This is numerical aperture, that is 2 pi by lambda into A into numerical aperture. This is called as V number. That is, up to this value of lambda, they are going to be propagated through the material. That's why it gives a cutoff for the lambda values, number of ways that are going to be propagated. Okay, and by making use of these numbers, okay, and if you take this lambda, it is going to have both positive or negative values. Okay, it is a propagation constant. That's why, as it is having two sides, for multi-mode step index optical fiber, the number of modes of propagation is given by v square by 2. For multi-mode graded index optical fiber is given by v square by 4. Okay. This is how we are going to use this v number for the calculating the modes of propagation. Okay. Now we are going to see optical fiber communication system. Any communication system consists of three parts: transmitter, propagating medium, and receiver. Here in the propagating medium, we are going to use our optical fiber materials or optical fiber cables. Okay. First, we are taking this one as transmitter. We are going to have just a block diagram representation. Okay, transmitter. It consists of, first we have to give a input signal to this one, then it takes this one, the form of analog form, analog signal in analog. Analog means electrical signal, just for our easy understanding. Analog signal. This input is converted to analog form of signal, where we are going to have voltages here. Then by using a coder, we are going to that one change that one into a digital form, where we are having only plus and minus, or true or false, or low or high values, like this. Digital signal in digital form. Signal in digital form. Then we fed this one to a light source, or LED or laser, so that the signal is converted into light signal. Then we go that one to a unit called as modulator. Modulate means to bring change, because we are talking about signals that are visible and audible for us. Hardly these types of signals can be sent through a distance of half kilometer. That's why they are not having high values of energies or high values of frequencies. In order to transport them through to longer distances, we have to mix these signals with higher wave frequencies. That process is called as modulation. That is, we mix with smaller frequency signals with higher frequency signals so that they can be carried through longer distances. Then we are going to use our optical fiber now. Here we are going to have a coupler where the optical fiber starts. It passes through some kilometers, and this is the optical fiber cable. Optical fiber cable. Then we are having a connector here. Then after the signal is passed through some longer distances, it is some kilometers in range. Okay, the length of the optical fiber cable is some kilometers in range. After passing through the distance, the signal is going to be weakened. That's why first we are going to have some repeaters between this transmitter and the last part receiver. Then this is called as repeater. Consists of amplifier. First we are going to amplify the signal, strengthen the signal. Then we regenerate that one, regenerator. That is, suppose if we are sending a signal like this, after passing through longer distances, it is going to be converted into a very weak signal like this. Then if we amplify that signal, we are going to get like this type of signal, not like this. Then we have to smoothen this one. This is called as regeneration. First we have to amplify this one and then we regenerate that one. And this is the purpose of this repeater. We are going to have so many repeaters between a transmitter and a receiver. We are just showing one of them. Then again we give this one to the, with the help of this is connector. This is coupler. Again we take a connector and we give to the optical fiber. Again it travels through longer distances in optical fiber. Then we are having receiver at the other end. Receiver. In the receiver, first we are receiving light signals. It is optical detector. Then optical detector. Then we are going to amplify the signal first. Amplifier. Then amplifier, both amplification and regeneration is done here. Then we are going to have a modulated signal here. Then demodulation. Here modulation we are mixing with higher frequency signal. We are removing signal. Now we are having the signal in digital form. That is this is optical, means we are using the reverse process here. Then amplification, then demodulation. Then we are having signal in digital form. Then we use decoder and we get a signal in analog form. Then we fed the signal to output device or a display device. This is how the communication system works. Okay, here we are having this one. This is sorry. Here we are having a coupler. Okay. In this way, we can, by making use of this optical fiber, we can transport these light signals easily and very fastly. Okay. Now, coming to the applications of this one, we are having the applications in communication systems, in sensors, in industries, in medical field, and whatever may be the field, we are going to use optical fibers there. That is, there are innumerable applications for these optical fibers. Mainly talking about the applications in medical field. Applications in medical field, they are mainly used in endoscopy. Okay, that is endoscopy. It consists of two coaxial layers of optical fibers. One to carry the light rays from a source to the object of observation, then the second cable from the object to the screen or our naked eye. Okay, that is, to take light rays we are going to use one optical fiber, to receive the light rays we are going to use another optical fiber. Okay, that is the composition of this endoscope. Okay, they are used in the treatment of ulcers, in the treatment of cancers, for in the treatment of cancers, and they are used for observing heart and respiratory system. They are used for the treatment of ligaments, cartilage, and parts like that, and they are going to be used in order to treat ulcers and for the functioning of this heart and respiratory system especially. Okay, these are the applications in medical field. And in spite of having these advantages, okay, there are losses of energy in these optical fibers. We call that one as attenuation. This loss is generally expressed in decibel or decibel per kilometer. Okay, that is called as attenuation. And we are going to quote reasons for the signal attenuation in these optical fibers. There are so many reasons. First one is impurities. Okay, then the second one is defects. Then the third one is absorption losses. Okay, the material, if the light energy is passing through the material, some part is going to be absorbed by this material. That type of loss is called as absorption loss. Okay, that if we talk about impurities, each and every material is going to have some impurities as well as some defects. Both they are going to be, affect the propagation of light. Then defects, impurities, defects, absorption, then bending losses. Whenever there is a bend between this core and cladding, we are going to lose some amount of light. Then transmission losses. While signal is going from one region to another region, depending on the conditions there, we are going to have transmission losses. That type of loss is called as transmission loss. Then scattering loss. Due to the particles there or the particles of the medium, okay, different particles are going to scatter the light in different ways. That's why we have to use any particle in the or we are making a material means some particles are there. Those particles, they are going to scatter the light. That type of loss is called as scattering loss. Then radiation induced losses. Depending on the radiation we are using to propagate through the material, suppose if we are using a red light and yellow light parallelly, then some materials they are going to allow red light easily, some materials they are going to allow yellow light easily. That is this type of loss is called as radiation induced losses. Then inverse square law loss. Suppose if a radiation goes from one point to another point in the presence of medium or in the absence of medium, it is going to be have some loss. Okay, as it is traveling, it is going to have some loss. We have to take that one into account. That's why we have to call that one as inverse square law loss. Okay. Then the last one is core cladding losses. We are referring some all these reasons. Parallelly, we have to look at the cladding also. Whenever this cladding is having all these types of losses, it is a loss to the signal. That's why the last one is called as core cladding losses. We are going to see these types of 9 losses in these materials. In spite of these types of losses, okay, in 1960s, Kyo, he proposed that, or he first told that we can reduce the losses due to impurities and we can bring the signal loss or attenuation in optical fibers to a value less than 20 decibels, for which he got Nobel Prize in 2009.